Um, okay, okay. Let's start this week's online tutorial. This week we're gonna talk about domain adaptation. Let's start from empirical risk and minimization. First, because we all know that empirical risk minimization is the foundation of machine learning, and it leverages the label of the data set. Then we minimize the empirical risk, which we can obtain from the training data. So we minimize the empirical risk, and under like certain assumptions, for example, the training data and test data, they are independently and identically distributed. Only under this case, we can say that our learning algorithm can be generalized to the test data set and pretty effectively. So this is supported by the famous PAC learning framework, and also the VC dimension framework. And remember that we talk about on the lecture that the empirical risk can generalize to the expectation is based on the law of large numbers. So if we can collect infinite number of training data, at the end, our empirical risk is equivalent to minimize the expectation of our model. So that way our learning model can fit to the training data well and generalize to the test data well. But note that this is only under the assumption that the training data and test data there's exactly the same training distribution, exactly the same distribution. So we simplify this as the IID assumption. But in real world scenarios, it's really hard to satisfy that assumption. For example, like we said, there are all kinds of different noises in the data set. Maybe the noises are applied to the input data, like the image. Also, it can be applied to the label. So in that case, it's gonna be the label noise problem. So whichever the case, our goal is we still hope that we can learn a perfect model that can generate to the test data well. So this is why we need domain adaptation. We have introduced there are two types of scenarios in our lecture of domain adaptation. The first one is covariate shift, and the second one is target shift. So these two cases, they are the covariate shift assumes that the training distribution for the data set for the input data X is different from the test distribution of the input X. But on the other hand, they have the same condition distribution, which is the probability of Y given X. And recall that the target shift assumes that they have different training and test distribution on the label Y. And the conditional distribution of X given Y, they are the same. So they are a little different, but similarly, we can use the technique called importance reweighting to solve the two problem. So there are basically if we learn this importance and apply it to the training distribution. In that case, if we minimize the risk, we can make sure that our learning model can generalize well to the test distribution, because we only focus on the examples from training data that is similar to the test data. So that's what we do. So that's a basic idea. But in this tutorial, we only talk about one certain scenario, which is the covariate shift. Like I have shown several examples here. For example, the first one is object recognition. We can say there are so many different styles of images. We have the real world images. We have the clip art. We have the paintings. So all of these different styles, they all represent the same object. They have the bed, the bicycle. But for example, so that generalized to real world scenario that in our training data set may sample from one distribution, but it turns out in real world scenarios, our test distribution is different from our training distribution. That's gonna be hard to apply our learning model. So in this case, it fits to the covariate shift very well. We have different probability distribution of X between the training distribution and test distribution. But we given certain features. For example, for the bicycle, we have the wheels. No matter how the style changes, how the distribution changes, we have the same the certain feature. We can know that it's probably a bicycle. So that's why their conditional distribution are the same. And secondly, there's a example of autonomous driving. We can see that if we want to learn a model that applies well to the autonomous driving scenario, but if we train our model and we based on the data collected from daytime images, and at the end, if we drive the car at night, or maybe we drive the car to a different place from the warm areas to the cold areas, and maybe even gonna have the snows, so the images will vary significantly. So that causes the distribution shift between training data the training data X from the test data X. So that is also very may seriously influence our learning performance. So that case is still a covariate shift. And remember, in this example, we have the same road. We have the maybe the same sign. When we see the crossroad, we have to stop the car. So that's why in no matter what kind of places, they have the same rule when you drive the car, similar rules. So that's why they have the same condition distribution. You can see that covariate shift is, I think, is more common than target shift. So it's in the modern machine learning research, we mostly consider the covariate shift. Nowadays, we call it a different term, which is called the domain shift. So you can see that different distributions, they're from different domains. But basically, they're just the same. They have the same assumptions. Okay. So let's see, if under this scenario, can we apply the famous empirical risk minimization, the ERM, to this problem and solve it? Obviously, it's not, because if we can obtain a model that achieves the minimum empirical risk on the training data, it's not gonna perform well on the test data. That's called that means that when we collect infinite number of training data, the limitation of our ERM model cannot be the optimal model for test data. So that's can be formed by equation 2. And the optimal model is the model that can minimize the generalization error on the test data. The test data is composed by a test example T, and its ground truth label U. So ideally we have this model based on equation 3, but actually in practice we cannot obtain this model. So how can we solve this problem? We have to, based on our training distribution, and learn a model that can perform consistently well by minimizing the empirical risk and can perform consistently well on the test data. Okay, this tutorial we talk about how can we solve this problem. But before we start, we introduced there's a technique called a cross validation. So why do we need this thing? Cross validation can help us analyze to estimate the generalization error, which is because normally if we train a model, how can we know it's good or not before we really apply it to the test distribution test scenario? So we have to split the training data set and hold out a part that we cannot use during training. We just use it as a validation. So in this case, if we obtain performance using this validation data set, and if it performs well, we can say that maybe it's really achieved the minimum empirical risk, and it possibly can generalize well to the test data. Still under the IID assumption, we can conclude based on all the theoretical support foundation. We can say that the model can the risk obtained from the validation data set, it can estimate the generalization error pretty well. So in that case, if we have n numbers of validation data, which the risk can be represented as R superscript n, then it actually is equivalent to the test error. So it can be explained by equation 4. So what we do is to make sure that there's no random factors to affect our result. So we do k-fold cross validation. Basically, it's just we do this similar process for k times. So we equally split the training data set into k folds. So if we have n training data, we can have k folds of the training data, and each fold have the n divided by k numbers of data. So every time we just choose one fold as our validation data set, and then we use the rest k-1 folds of data as our training data set. And then we minimize the empirical error and obtain our optimal learning model. Then we test our performance on this the holdout validation data set. Then we can have one risk based on this split. Then next time we change to another fold and use it as our validation data set. So in that case, we can have k risks in total. Then we average the validation risk obtained from these k scenarios. And then we can say that the averaged risk is a good estimation of the test error. Then if we like generalize to the k-fold to leave one out scenario, so this leave one out cross validation is a special case of k-fold cross validation. When if we have n numbers of training data and we split the training data to n folds, so every folds they have just one training example. So that in that case, just leave one out cross validation. Still, we can conduct this whole process for n times, so that if the training data is very large, we can the result is gonna be averaged over all the n repetitions or n iterations. So in that case, the estimation of the generalization error is gonna be is more effective than k-fold cross validation. There is a theoretical proof that we can conclude when we have n numbers of training data and when we use the leave one out cross validation, the error, the estimated generalization error is actually equal to the test error. Yeah, but remember that this is cross-validation technique can only be used under the IID scenario. Still, we have to assume that training dataset and tested dataset, they are the same. But obviously, when we consider real-world problem where we have covariate shift, the cross-validation dataset, cross-validation technique is not working this time. So how can we decide our optimal model and we choose one that can generate well to the test distribution? So in the following, we first we revisit this importance reweighting technique to tackle the covariate shift. Then we introduce that importance weighted version of cross-validation that helps us to estimate the generalization error more effectively and more accurately. So importance reweighting technique is pretty simple. If we want to make sure that we learn a model based on empirical risk minimization, and it performs consistently well on test data, we just have to make sure we make a transformation to make sure the transformation of training data distribution is same as the test distribution, which is we can achieve by equation 8. So here we learn this weight beta x. So beta is a function of x, and we apply this. We think of it as a importance, and we apply to each example of training data. In that case, hopefully we can, if the beta function is pretty accurate, we can say that the transformation can perfectly fit the test distribution. So if we want to know this beta distribution, this beta function, we can do a transformation. So we have this one. In real world problem, we can estimate. We use the distribution estimation. We can estimate the test distribution and training distribution. Then we can further obtain this beta function. So, but the estimation is actually outside the scope of this course. So in the following, we just assume they are also we have access to these two distributions. Then, if we further we want to minimize our the objective function based on this training data, we can just apply this importance to the loss value, which is formed by equation 9. So we name that under this optimization strategy, under this one, we can obtain a importance weighted ERM model, which is defined by this, the theta IWERM. So in this case, when we minimize this importance weighted objective function, our model can actually be consistent to the test data. In this case, the equation 10, it holds true. So it means that when we collect infinite number of training data set, our learning model based on this importance weighted strategy, we can make sure it equals to the optimal model, that the optimal model from the test data set. I have been talking about consistency a lot. The consistency is that it means that when we just no matter no matter what objective function we choose, we just want to learn a model from training data set. We hope that the training set, this model is consistently performs well on the test data set. So that's the consistency. But there's a problem that if we apply this importance weight to our loss function, so we only focus on there's small amount of training data set that is very close to the test data set. So in this, intuitively, because we only focus on few examples and we lost a lot of knowledge, some training examples are ignored by us. So we actually lost a lot of knowledge. Remember that we have the PAC learning framework. If our training data becomes smaller, it actually it's not the hypothesis class is getting more complex and it's more hard to learn an optimal one. So when we apply the PAC learning form to this case, if there's under the extreme scenario that training distribution and test distribution, they're dissimilar to each other. So their similar examples between them is going to be so small. In that case, our hypothesis class is going to be super complex and super has very the hypothesis class is going to be super unstable. So which means that if we have we train the model for various so many times, the result is going to be so different. It will have a very large variance. So that's why the importance reweighting technique is not stable in practice. So then we have to have this trade-off between consistency and stability. How can we achieve that? It's because the importance weight, maybe they are too much. They only focus on a few training examples and they they assign the too small value on the rest on less important examples. So we want to weaken this effect. So first we can do, following the equation 11, we can apply this power of lambda to the importance weight, this term. Also, we can add a regularization. We make sure that we make sure the learned hypothesis class is less complex. And in that case, it can generalize well. So both two strategies, they works well, but yeah, but to without loss of generality, we just focus on the first one. We use this power of lambda to weaken the importance effect. So then we can have, if we want to tackle the covariate shift problem, we can just use the equation 11. So, and we can control this lambda factor, lambda hyperparameter, and find the best learning strategy and find the best model that performs well, both just perform well on the validation data set. In that case, it can perform well on the test data. Then another problem arises. How can we choose this lambda hyperparameter? Normally, when we want to estimate the generalization error, we can use the cross-validation technique. And we can also conduct parameter tuning and also model selection based on this cross-validation technique. It's because our final goal is to generate well on test data. So we have something to choose and something to adjust. We can do it on this validation data set. So in this case, if we want to find an optimal lambda, so we use the validation data set and we choose different values, and we find the best one that performs the lowest validation error, and then use it as our final model and apply it to the test data. So that's what we do. But still, we have this covariate shift problem. Remember that when we want to do the cross-validation, our validation data set is actually from the training data set. So there is still a gap from the validation data set and the test data set. So if we do the model selection or hyperparameter tuning, the best model is not gonna be performed the best on the test data set. It's still the best one on the training data set, which under the covariate shift case is not optimal. So how can we solve this? Yeah, so it's pretty simple, and we just do the importance reweighting all over again. Just apply it to the cross-validation data set. So although that's very simple, but it's very effective, and it really helps to choose our model and hyperparameter. Then what it does is simply can be formed by equation 13. So when we have this validation dataset XY, then we apply the importance to each example and then calculate its loss value. Then finally, the average from all different folds, from all different K folds, then have the final validation error. So it's this one. Mm. Although it may seem very simple, but still we have the theoretical foundation to make sure that this strategy is actually safe and we can use it. And the result is that when we conduct this kind of importance weighted cross validation, the estimated error is actually equivalent to the test error. So so it's the conclusion is equation 15. We have the proof, but at the end, but it's optional. So if you are interested, you can feel free to have a little derivation by yourself. Okay, then we show simple example here to help you understand the covariance shift and importance revealing better. Let's first, we want to create this covariance shift problem. So we assume that we have the different probability density functions to sample our training data and test data. So the training data set is from sampled based on this normal distribution. It has the mean of 1 and has the deviation, standard deviation of 1/2. And we have the test distribution whose mean is 2 and whose standard deviation is 1/4. So we can say that this is actually, they are disconnected. They have, if you visualize this distribution, they don't overlap much. So we can say this problem is is called extrapolation. We learn from a distribution and then we apply it to a completely different one, which means that most of the data, they are not overlapped and they are new, complete novel. We haven't seen before. So that's called extrapolation. Yeah, remember that normally we assume that we can have access to this two distributions. Even if we don't have them, we can do like use the very common density estimation techniques and to make sure we get these distributions. But yeah, we just assume we already have them. Then after, we want to know the importance. Yeah, if we want to calculate their importance, which is very easy, like we said, showed before, we just use the distribution of test data to divide it by the training data. So in this case, we can have we can actually plot the ratio here. Yeah, it's showing on the left figure. One thing to notice is that we can see that most of the training data, which is shown by the blue line, most of the training data, they actually have very, very small ratio, small importance. So that means most of the training data, we just ignore them. We only focus on very, very small part of the training data. So we lost many knowledges. So that's why we said before, we need a trade-off between consistency and stability. Yeah. Okay, let's proceed. Still, we have the training data distribution, test distribution, and we assume our condition distribution, they are the same. In this case, we just we can use any function to conduct our problem. But we use this sync function. Sync function we can show here. So it's the green line. It's like this. Our goal is to learn a model that fits well to this green line. So that's our regression problem. So then we have our target, which is the sync function. And when we want to generate data, so we first we have the sample density function in equation 16 and 17. And then we input this data and to the target function, and then we can have our target y. But we want to do it more realistic. We have the random noises applied to our sampling. So we assume this random noise follows the normal distribution, having mean and zero mean and a quarter 1/4. standard deviation. So when we really do this sampling, we can have show the result here. So you can see there are so many, it's not aligned on the target function very well. Then when we want to choose a hypothesis class as our model to learn this to tackle this problem. So here we choose a relatively simpler one. So it's a linear regression model. Is shown by equation 20. So you can see it's actually just a line, a straight line. It cannot fit to the target function very well. So then we want to learn the model. We minimize objective function. Here we can just employ the least square loss here, and we apply it with our importance reweighting here. Then if we just let's see the empirical risk minimization scenario, which is we have the lambda equals to 0. So in that case, we don't apply the importance to the training data, and then we train this model, and we actually have this straight line. It's like this. It can fit to the training data pretty well, but if we have different distribution of test data, which is shown by the red dots, red crosses, the test performance is actually very bad. So then if we gradually control this lambda, so gradually increase this lambda, we can see that it's showing here, our learning model fits to the test data better, because you can see around here, the model fits to the test data, fits to this target function around here is much better. So importance reweighting is actually pretty effective on tackling the covariate shift. But remember, we have to choose the best lambda. If we we choose this lambda based on the importance weighted cross validation. Then we conduct a k-fold cross validation for k times. We have k values of validation error. If we visualize all the variables from test error, cross validation error, and importance weighted error, we can show that we change the value of lambda, and we show the result here. We can see that when we gradually increase the lambda, the test error is indeed decreasing. But also the importance weighted cross-validation error is decreasing, but the cross-validation error is increasing. So that's not true for our case. We hope that the validation error changes similarly as the test error. In that case, we can make sure we find the best model that generates well to the test data. So that's why importance weighted cross-validation is better. But there's one thing to notice. You can see that at the beginning, when we have small lambda, the standard deviation of the error, they are very small. But if we have very large value of lambda, the standard deviation gradually increases. So that's why when we have large lambda and large importance reweight, the performance of our learning model is gonna be unstable. So actually, it's not, when we want to choose the best lambda, it's not gonna be the larger the better. It's better to have a model that performs more stable across different scenarios. So based on these figures, it's actually around 0.6 to 0.8, the lambda is better because you can say that it's more stable compared to lambda equals 1. And for this case, even in some cases, the performance is increasing, the error is increasing. So that's what we want to avoid. So maybe choose the 0.8 is better. So that's the basic idea of importance weighted cross validation. We also provided code for this tutorial, and it guides you through this toy regression problem. And you can just run by yourself, and you can understand this problem better. We also show the closed form derivation of the linear regression. It teaches you how to get the learning model just by one step using the closed form.
Yeah,
Yeah.
maybe it's good for us
Yeah.
to quickly go through the code, maybe in 5 minutes.
Okay. So
Okay.
yeah. So this is the code. First we run it and we generate this the density, and there also this one.
Maybe you have to share the screen.
Okay.
Okay.
So okay. So there are just first the generate data. We have this data density, and sorry, I run it again. And then we generate this one. We have the data, have the target, and this is the closed formed solution of our linear model, and we have the result here. And then when we have the ERM, we can obtain this learning model which only performs well on the training data. It cannot perform generalized to test data. Then we tune the value of lambda. We can see that it gradually, as the lambda increases, the learning result fits to test data better. And then we want to use the importance weighted cross validation to conduct our parameter tuning. So in this case, we conduct the k-fold importance weighted cross validation and average the result and compute the standard deviation. And then we have, sorry, we have to run all the results. So then we can have this result, which is the same as the slide. So all the result, all the detailed code, you can check it by yourself. For any further questions, you can ask us on the ad discussion. So that's all. Okay.
Yeah, I'll just stop
Finish.
recording. Yeah.
Yeah.